Hi, welcome back to Math 112. We're going to talk today about section 8.4, which is all about vectors. Now, vectors are kind of how we describe the world. Vectors are quantities that have both a length and a direction. Think, for example, about velocity. Generally, we talk about objects traveling or cars. Let's say you're going to Portland, you're driving at 55 miles per hour. But that doesn't really tell somebody anything about which direction you're going until you say east. So this is an example of a vector velocity, or velocity expressed as a vector. In other words, this velocity doesn't make much sense until we give it a direction and a magnitude. Bearing on a map, forces, these are all examples of vector quantities. As I said, the length of a vector is called the magnitude, and we have to account for both the magnitude and the direction when we're doing math or solving problems. So let's take a look at an example here. One example of vector addition is a woman who leaves home, or a man, it really doesn't matter. This example says woman. And she walks 3 miles north. So that's this first vector. And then she turns and walks 2 miles southeast. Southeast is 45 degrees south of east. And if we want to know her straight line distance and direction from home, we add these two vectors together. So to add vectors together, it really doesn't matter which one we start with. We pick one and we put its tail in a spot, and then we place its head according to its magnitude and direction. In this case, this is 3 miles due north. And then we take the second vector and put its tail, so the tail is the starting point, at the head of the first vector. So we arrange our vectors head to tail, and then we connect our starting point with our ending point. Now, we can solve this graphically, right? We can use the law of cosines to find this distance c. We'll call this angle gamma. And let's say this is side A, and this is side B. Right, nothing new here. The law of cosines tells us that c squared is equal to a squared plus b squared minus 2ac times the cosine, 2ab times the cosine of gamma. So plug those in and we get c squared equals 3 squared plus 2 squared minus 2 times 3 times 2 times the cosine of, now this external angle is 45, so that means this internal angle is also 45 degrees. Solve this and we get that c equals 2.12 miles, right? But now we need to know an angle, and we will always describe our vectors with an angle from, from standard position. What we're actually going to find is this internal angle using the law of sines, which tells us that the sine of gamma divided by c is equal to the sine of beta divided by b. We can solve this. We know gamma is 45 degrees. We now know c. We're looking for beta. We know b. And what we end up with is beta is 41.7 degrees. This guy here is 41.7 degrees. And this guy, that means this angle here is 48.3. degrees. So what this means is that if somebody was starting from home and trying to get to this woman's location, they would go 2.12 miles at a bearing of 48.3 degrees north of east. You can see how the vector describes very precisely this woman, this location. But you can also see that we could not just add together 3 miles and 2 miles and get 5 miles, because although she walked 5 miles, her actual straight line distance from home is not 5 miles. Okay. That's kind of the hard way, although we do it that way sometimes. It depends on how our vectors are described. So this is that same basic triangle. The other way we can talk about vectors is in terms of components. So this vector here that was 3 miles long due north. We know that this represents a vertical displacement of 3 and a horizontal displacement of 0. So the other way we can describe this vector is as x, where x is the horizontal displacement. That would be this guy. That'd be, well, x2, right? And then the vertical displacement, which is 3. Okay. Now, this guy here would be a little harder to do this with because, well, we could do it. This is 2 miles. So we can use trigonometry to relate our x and our y. So this is vector 2 here and vector 1. So we could find this x2. That would be, remember this is 45 degrees. So this horizontal displacement would be 2 times the cosine of 45 degrees, which would just be square root 2, right? And this guy, this y, would also be square root 2. So then, and this guy was 3, so we can get to this horizontal, or this vertical displacement would be vector 1, which is 3. This is actually a negative square root 2 because it's down. 3 minus square root 2. And the x2 would just be square root 2. So our vector to get home, or from home to the ending point, our vector sum would be square root 2, comma 3 minus square root 2. I hope you see what I did. What I did there was I defined each of my 2 vectors in terms of components, and these components represent horizontal and vertical displacement from head to tail, right? And once we define our vectors in terms of components, we can just add up the horizontal components and add up the vertical components. And we know how to find those because we can use trigonometric relations to find vectors from bearing and magnitude. Or sorry, find components from bearing and magnitude. So let's practice that. Let's take a look at this vector, which has got a magnitude of 10 at an angle of 30 degrees, and I want to find the components. This is just a right triangle. So x is equal to 10 cosine 30 degrees. Y is equal to 10 sine 30 degrees. The sine of 30 degrees is 1/2. So y is 10 times 1/2, which is 5. The cosine of 30 degrees is root 3 over 2. This is 5 square root 3. So this vector could also be described in terms of components. We use this kind of a bracket, and it's the x displacement, y displacement. Okay, one more. Backwards this time. Let's find the magnitude and angle of a vector with components -4, 3. So I've built my little triangle down here. This is my starting point, which I just labeled 0, 0. You can label it whatever you want. 0, 0 is convenient. My x component is -4, which means I've got a run of 4 to the right, or sorry, to the left. And then my y component is 3, which means I've got a rise of 3. We can use the Pythagorean Theorem to find this c. The c, this distance here, is the magnitude. So c squared equals the square root of -4, yeah, all right, squared, plus 3 squared. 16 plus 9 is 25. Square root 25 is, sorry, c equals the square root of, so c equals 5. So my magnitude is 5. From here, I can find my angle relatively simply. I called it gamma. Alpha would be better. Doesn't matter. That is going to be the inverse sine of, 3/5, which is 36.9 degrees. But now remember, we want to define this from the positive x-axis. So our angle theta will be 143.1 degrees. So our vector will have magnitude 5 at an angle of 143.1 degrees from standard position. Okay. Oops. Here's a more practical example. You're trying to move this object, whatever this object might be, and you're trying to make it go forward. And you're wondering, well, you're pulling with a force of 30 pounds. So that force is our magnitude. That is a vector quantity. You're pulling upward at an angle of 20 degrees. And you're wondering how much of that 30 pounds force is actually helping you move forward. Well, what you're really asking is, what is the horizontal component of this 30-pound vector? So that's my x. X is equal to the magnitude times the cosine of the angle with the horizontal. Take out your calculator and run this through, and it turns out most of your force is going the direction you want it to. Now, the steeper this angle, the smaller the portion of the applied force that is horizontal. So if you really want to move something forward, you want to keep your angle shallow. Okay? All right, let's try another one. So I've got two vectors here. I've got vector u that has got a x component. Well, this isn't actually u. Okay, so I've got a vector u that has got an x displacement of 5 and a y displacement of 4. And a vector v that has an x displacement down 2, or to the left 2, and a vertical displacement of 3. But I want to scale these things. I want to find 2 times vector u minus 4 times vector v. That's okay. Scalar multiples, we can just multiply our individual components by our scalar multiple. So this is actually what I have on this diagram is 2u. We've got a horizontal displacement of 10 and a vertical displacement of 8, which is 2 times 5 for the horizontal displacement, 2 times 4 for the vertical displacement. And I've got a vector v multiplied by 4. This is actually, so this is 4v. Now what I'm showing here, okay, this is all right. Then the minus sign would just reverse the direction. We're not going to worry about that so much. So to do this, we are just going to add our components. Actually, we're going to subtract our components. So 2u minus 4v is equal to 2 times 5, 4, minus 4 times negative 2, 3, which is 10, 8, minus, 8, negative 8, 12. Now, we just subtract our components. So 10 minus negative 8 is my x displacement, my horizontal displacement, and 8 minus 12 is my vertical displacement, or I get 18, negative 4. And that's actually what this purple vector is. This purple vector describes the vector that is 2u minus 4v. So vectors are actually very handy critters. All right, this is a short video, so we're going to just do one last example. This one kind of illustrates the power of vectors. So maybe you're on a treasure hunt, maybe you're just out on a hike, whatever. You walk, you know that you walk 5 miles north, and then you turn left 30 degrees and walk for 4 miles. So we went 5 miles due north. So this first vector has got a horizontal displacement of 0 and a vertical displacement of 5. And then you take a turn, something strikes your fancy, and you turn left for 30 degrees. And you walk for 4 miles. And then you just think to yourself, well, maybe I should get back on my original track. So you turn 90 degrees and walk for 3 miles. And then you turn right 45 degrees and walk for 2 miles. And now you want to go home. Go back to your car. Okay. What angle should you turn at here? Well, let's figure this out. We can do this with vector addition. So what we're going to do is we're actually going to put all of our vectors in component form. So this guy that has a magnitude of 4 miles at an angle that is 30 degrees to the left of vertical, we can figure out his horizontal and vertical displacement from his head. So this is his head. His tail is up here. Head, tail, right? So this vector 2 has got components. The horizontal component is 4 sine 30. So let's see, let's do this. This is 1, this is 2, this guy will be 3, this guy will be 4. So we can describe vector 1 in components as 0, 5. Vector 2, the horizontal component is the magnitude, 4, times the sine of 30 degrees. The vertical component is 4 cosine 30 degrees. Now be careful here. We're going to the left, so my horizontal displacement is negative. Vector 3. So we made a 90-degree turn here. What that means is this angle here with the horizontal is now a 30-degree angle. So my vertical and horizontal are described as This time we're going to the right so that my horizontal displacement is positive. So 3 cosine 30 degrees for my horizontal, and 3 sine 30 degrees for my vertical. Vector 4. Okay, this one gets a little tricky. All right, we know that we've got an angle with the horizontal of 30 degrees. We turned 45 degrees. So we've got a total of 75 degrees. So this is a negative 15 degrees from the horizontal. That'll work. Actually, we're just going to call it 15. Okay. So its horizontal component is going to be magnitude, which is 2 times the cosine of 15 degrees. And the vertical component is down, so it's negative 2 times the sine of 15 degrees. Okay, so now this vector here, what we're going to end up finding is its vertical displacement, which is its y, this is actually 5, x5, and this vector is the sum of all of the other vectors. And it will be headed back to home because we arrange all of our vectors head to tail. We kind of close a circle. So V5 is V1 plus V2 plus V3 plus V4. We can find the x component as 0 minus 4 sine 30 degrees plus 3 cosine 30 degrees plus 2 cosine 15 degrees. And when I prepared my notes, I actually messed this up, so let me get a calculator. This is what I want. Okay, so I've got 30 degrees sine times 4 negative 30 degrees cosine times 3, add that, and then add 2 times the cosine of 15 degrees, and we get an x displacement of 2.53. All right, so I'm going to erase some stuff because I need some space. So now we're going to find my y. We're going to find y5, which is y1, which is 5, plus y2, which is 4 cosine 30 degrees, plus y3, which is still a positive 3 sine 30 degrees. And then we're going to subtract y4 because it's negative, so 2 sine 15 degrees. So 5 plus 4 times the cosine of 30 degrees plus 3 times the sine of 30 degrees. Sorry, I think I messed that up. Let's try that again. 5 plus 4 times the cosine of 30 degrees plus 3 times the sine of 30 degrees minus 2 times the sine of 15 degrees, and I get 9.44. 9.45, we'll call it. Okay, but what do I really want? What I really want is this angle, right? Well, I can get that because my angle, we'll say it's theta. The tangent of theta is y over x, so theta is the inverse tangent of 9.45 over 2.53, which gives us 75 degrees. Okay, so that's the angle with the horizontal, right? What do I really want? I really want this angle right here, yeah? Well, I can do that. If this is 75 degrees down here, means if I pull this thing all the way out and I break this apart, so this, put in a horizontal, this angle with the horizontal is 75 degrees. This angle here, remember, is the same as that one, so that's 15 degrees. So that means we need to turn 15 plus 75, 90. So we need to turn 90 degrees to the, I'm facing this way, left. Okay? All right. That's it for today. Have a great rest of your day. I will see you all soon, and in the meantime, do good math.